This is a match. It's a chemical prison that locks up chemical energy that's set free. All it takes is a strike on a matchbox. Understanding how reactions like this work has sent human beings out of this world. But nearly 50 years after people first ventured into space, it's still far too expensive. Every shuttle launch burns up more than $400 million. There must be a cheaper way. Around the world, a new generation of rocket pioneers is fired up by the challenge.
This is a small piece of the rocket propellant that we used, and it's held together in a rubber matrix, so it's really quite flexible. So I'll just ignite a piece.
This propellant is the same stuff that burns in the Space Shuttle's booster rockets. Steve Bennett hopes that experiments with it will help build a rocket big enough to take him and his friends into space. It's a serious business. If they prove they can do it reliably, they could win a competition set up by an American millionaire. It's worth $10 million. There's a long way to go, but Steve's already got years of experience. Back in 1993, it was just a hobby. Steve and his family went out at weekends to launch rockets for fun. They just wanted to see how high the rockets would go. This is how all the great rocket pioneers started out.
I got into it at a very early age. When I was a kid, I used to watch these Gerry Anderson films, the Thunderbirds and that sort of thing. And even now, when I watch the films with me 3-year-old son, you know, the music, you know, you get the drums and all the rest of it, and it just gives me a sort of buzz, you know. It makes me want to build rockets.
Steve set to work in his garage. He knew it would take all kinds of science, but the key would be the right kind of chemistry.
We have liftoff. We have liftoff.
This is a strip of magnesium metal. Drop it into hydrochloric acid and watch using a heat-sensitive camera. Blue is cold, purple is warm, yellow is hot, white is even hotter. Clearly the reaction releases heat. It's exothermic. So it's the same kind of reaction that powers a rocket, even though there are no flames. You don't even need solid chemicals for an exothermic reaction. The water in this beaker is at room temperature, but add another cold, clear liquid and a bubbling reaction starts immediately. The heat-sensitive camera reveals gas being given off. It shows up because it's hot. The heat seems to come from nowhere, but actually it was locked up in the chemicals all along. Chemists show what's going on in an energy level diagram. Imagine this ball represents the reactants, the chemicals that go in to start the reaction. Before they start reacting, there's this much energy in them. As the reaction begins, it starts to make new chemicals, products plus heat. The products only lock up this much energy because some of the energy that was in the reactants has been given out to the surroundings as heat. Exothermic reactions always work like this. The products have less energy than the reactants, so the energy left over heats up the surroundings. By 1995, Steve's rockets were starting to get more sophisticated. Instead of crashing down to Earth, a parachute should make this one float down so it can be fired again.
This is ready for the test firing of the parachute ejection mechanism.
It worked. Hundreds of people came to wish Steve good luck for the countdown.
We bless in the name of God, the Father, the Son, and the Holy Spirit. The rocket.
We have liftoff. We have liftoff.
It went very well. I was over the moon with that. The launch was a total success, and now I'm well on my way to my next launch.
Fired up with success, Steve no longer worked alone. A team formed to ready the rocket for another mission. By 1997, the rocket had left Steve's garden far behind. Now at Salford University, the team had the right kind of kit to start recording rocket launches scientifically. They could figure out what was holding them back and how they could fly higher.
The computer software shows a maximum altitude of just over 5,500 meters at about 30 seconds into the flight. We've also got 4.9 seconds of supersonic flight there. The rocket goes supersonic 3.2 seconds into the flight and comes out of supersonic around about 8.1 seconds. So we went faster than the speed of sound with that one.
Ignition.
The rocket fuel is burning its fiercest about 2 seconds after ignition. At this point, the pressure is built up to such an extent that you're getting the maximum benefit of all the expanding gases rushing out of the base of the rocket.
All that gas and energy comes from two simple chemicals. Mixed together, nothing happens. Like a lot of chemical reactions, they need a little help to get started. Add a little energy. Rocket fuel needs a bit of heat energy to light the fire of the big reaction. It would be dangerous for Steve to set off his rockets like this, so he uses a special igniter. It works using heat from an electric current. That means Steve can stand a safe distance away, sending the current down wires from a battery.
I can demonstrate exactly how these work by passing a current across the tip of the igniter head there, which contains a paragen, which is a kind of miniature explosive. So here goes.
Steve checks the ignition system using a block of old fuel. It might not burn properly in a rocket, so it has to be destroyed. Even though it's old, there's still a lot of energy locked up in there. The trick is to release it in the right direction. Burning like this, the energy shoots out in all directions, so there's no rocket effect. But inside a rocket motor, all the smoke, gas and flames will be channeled one way, down. So the rocket is propelled the other way, up. Several different blocks of propellant must ignite in the right order. If they don't, Steve knows the rocket will misfire. It won't take off, or it will zoom in the wrong direction. So he has to understand exactly how the exothermic reaction starts. Again, an energy level diagram shows what's going on. Overall, this is an exothermic reaction. So the reactants have more energy than the products. But this time, before the reaction can start, there's a barrier to overcome. It needs a little extra energy from outside to kick the reactants over the top of the energy barrier before the reaction will go. The amount of energy it takes to get going is called the activation energy. Provide that, and the reaction makes it over the barrier and products can start forming. Once it starts, there's no going back.
We have liftoff. We have liftoff.
It's a big day for Steve's team. Early tomorrow morning, they plan to launch their most advanced rocket ever. It will stand 6 meters high. There's a lot at stake. Several companies have paid thousands of pounds to light the fuse on a successful launch. If everything works, Steve will probably get more money to build more rockets. But if this rocket misfires, the dream of getting into space might stay just that, a dream. Trouble is, rockets don't always work.
5, 4, 3, 2, 1, ignition.
And that wasn't the only time.
Britain made another brave bid to enter the space race today from a launch pad in Devon. The idea was that Star Chaser 3 would reach 15,000 feet in an experimental program devised by Salford University's Space Department, but it didn't go quite according to plan.
One, ignition.
It should have soared 15,000 feet in 34 seconds.
Here we go. We have liftoff.
It was over in 10.
Bloody hell.
Full of rocket fuel, the Moore quickly caught fire. Rocketeers turned firefighters as the blaze quickly engulfed 2 square miles.
You've got to get some sleep.
Well,
I've got a couple of hours.
sleep in a car. I'll sleep in the van going up there.
While you're driving.
Me.
It's the night before launch. Steve must give his final briefing to the team.
Right. Listen, folks, this isn't a lecture, right? So we're going to stand around the table again, yeah? That means you can get out of your seats and you come around here.
There's a lot to remember.
This is what I propose to do. Leave the university between 3 and 3:30 in the morning with a view to getting there for about 5 o'clock. Vehicles, you've got a 7.5 ton van, helicopter, fishermen and tractors. Okay, so the launch coordinators, that's all the people with radios. They're all also going to wear white hats unless you're first aid, okay? First aid has green hats. Now we're going to have a bunker about 100 meters from the actual rocket.
This is where they'll press the launch button.
Once everything's in place, the rocket's on there, and all the metalwork's done, then we kind of switch roles, and our role then isn't so much as assembling stuff, it's one of expecting the press, and it's anticipating what the press are going to do and say.
It's a 6-meter rocket. It's made out of fiberglass and aluminium, various composite materials. Do you want me to look at where I'm pointing? No. Okay. Right, we need to move off. Okay. We've got a launch window of between 10 and half past. Unless we launch between that launch window, you're going to have to go home, yeah?
5 minutes to go. Everyone's energy is building at the launch site. Inside the rocket, a different kind of energy will be released when the propellant burns. To really understand exothermic chemistry, you have to zoom in on the individual atoms. The way rocket fuel burns is complex. You can see what's going on more clearly in a simpler exothermic reaction, when natural gas burns in air. Natural gas is methane. It's made from 1 carbon atom bonded to 4 hydrogen atoms. The bonds are forces that attract the atoms to each other. They don't want to let go, but when the heat comes on, things start to change. Heat provides energy to break the bonds, not just in the methane, but in the air around it too. Eventually, the methane molecule does split apart. Meanwhile, oxygen molecules in the air are also split apart by heat. Once that's done, the atoms are free to form new bonds. Forming new bonds makes the reaction products, water and carbon dioxide. But those molecules don't need all the energy that their individual atoms had when they were free. So making bonds releases energy. If making the bonds in the products releases more energy than it took to break the bonds in the reactants, the spare energy comes out as heat. Overall, the reaction is exothermic, but not all reactions work this way.
We have liftoff. We have liftoff.
Chemical reactions that absorb energy are called endothermic reactions. They're the exact opposite of what happens in a rocket, and much less common than exothermic reactions, but they can still be quite dramatic. These 2 dry powders are barium dihydroxide and ammonium thiocyanate. They're both very toxic, so this demonstration is rarely performed. When they're mixed together, each is at room temperature. Look through a heat-sensitive camera, and black shows that the temperature is dropping fast. In seconds, the temperature crashes down, eventually hitting -30 Celsius. Even so, the dry white powders have turned into a liquid. It's so cold that water vapor in the air freezes on the outside of the metal bucket. If If you put in a pack of plastic pockets containing water, give them a quick stir, you can make instant ice. Sometimes that's really handy. When she's not looking after Britain's Olympic athletes, Linda Mitchell takes care of Brunel University's women's football squad.
When the injury immediately happens in football, I would run out onto the pitch to make an assessment, and I would probably use an instant ice pack to give some cold to the area.
Inside the pack are dry ammonium nitrate crystals and a small bag of water. Break the bag open and the reaction starts. The heat-sensitive camera shows the water as yellow. It's quite warm. Black shows where the mixture is much colder, as the endothermic reaction between ammonium nitrate and water takes heat out of the beaker. Quickly, it's down to just 5 Celsius, as cold as a fridge. Again, an energy level diagram shows why. Remember, in exothermic reactions, there's more energy in the reactants than there is in the products. Overall, heat energy is given out when the reaction goes ahead. But in endothermic reactions, it's the other way round. The reactants have less energy than the products. That means the reactants have a huge energy hill to climb for the reaction to go ahead. They must steal the energy they need from the surroundings. That's why the temperature drops. At the launch pad, Steve's team have checked and double-checked everything. All they can do now is hope.
Roger, all launch coordinators are go for launch.
Launching in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Steve, you're like a happy man. That went really well.
It's everything up there, everything did exactly what it was supposed to do, and we got it back okay.
Steve's not made it into space yet, but he's on the way.
The next stage is to actually send a rocket up that's capable of carrying a pilot into space, and we're working on that one now.